This video is about enolate alkylation. Enolates can be used as nucleophiles, and they can be used to attack electrophiles in an SN2 substitution, usually with methyl or primary electrophiles, and they can also be used for nucleophilic addition or nucleophilic acyl substitution reactions with other carbonyls. An example of an SN2 substitution reaction with an enolate can start with a carbonyl compound with an acidic alpha proton that can be used to form an enolate upon treatment with base, and then the enolate is treated with an electrophile such as methyl iodide. In the first step, with sodium hydride, deprotonation occurs to form the enolate. Upon treatment with methyl iodide, the enolate attacks in an SN2 substitution to form a new carbon-carbon bond. There are two reactions that are commonly associated with enolate alkylations. The first one is the acetoacetate synthesis. In the acetoacetate synthesis, traditionally ethyl acetoacetate has been the starting material. However, any compound that has a beta-ketoester functional group can undergo this synthesis. Overall, what we're doing is we're taking these two acidic protons here, performing enolate alkylations in two steps, and then we are removing this ester group. So let's look at how this works. If we take ethyl acetoacetate, and we know we've got two acidic protons here, we're going to treat it with sodium ethoxide, a good base, and then follow that with an electrophile. We can do an overall SN2 substitution, and our compound is going to have an R group incorporated here. So we've made this new carbon-carbon bond. In the second step, we can do a second enolate alkylation. So we're using the same conditions. We can use a different electrophile if we want to put a different R group in, and what's happening now is we're putting our second R group and making another carbon-carbon bond. In the final step, what we're doing is we're converting this ester to the corresponding carboxylic acid, and then we're doing a decarboxylation. We can form this carboxylic acid either in this step with acid hydrolysis or in this step with base saponification. If we use base saponification, we need to then follow it with strong acid and heat, and that is going to remove the elements of carbon dioxide in order to form this final product. In this reaction, remember that the R group can be anything that allows for a good SN2 reaction, so a methyl, primary, allylic, benzylic, or anything with a good leaving group that's not too sterically hindered. Again, overall, we have taken a beta-ketoester and we have converted it into a mono or disubstituted methyl ketone. Now, if we use just one enolate alkylation, we end up with a mono substitution. If we want to put in two different R groups, we can get a disubstituted methyl ketone. So the mechanism of the acetoacetate synthesis is deprotonation to form the enolate, followed by alkylation using an SN2 reaction, and then we repeat that if we want to put in a second R group. So this is an enolate formation and alkylation, followed by an enolate formation and alkylation, and then finally we do an ester hydrolysis and follow that with a decarboxylation. We can do steps 3 and 4 all together if we use strong acid, water, and heat, or we can do a base saponification and follow that by strong acid and heat to do the decarboxylation. Now let's look at the mechanism of decarboxylation. Under strong acid and heat conditions, we're going to expel this carboxylic acid out as carbon dioxide. So in that case, we can draw our lone pairs in, and we have this bond kicked down. That's going to form carbon dioxide, which breaks this bond, and this oxygen is going to grab that proton. And so our intermediate is this enol, and we can draw the resonance form, which has the negative charge localized on this carbon. Now this reaction will only work with an electron withdrawing group next to the leaving carboxylic acid. And you can see why. You generate a negative charge at this carbon, and so you need this electron withdrawing group here, which can stabilize this negative charge. And so this negative charge is stabilized by formation of the enol, which then can tautomerize to the ketone. Additionally, of course, you have formed carbon dioxide. And of course, remember that this negative charge is stabilized by resonance, and usually you will need a carbonyl or some electron withdrawing group at the beta position of this leaving carbon dioxide unit. The second reaction that's commonly associated with enolate alkylations is the malonic ester synthesis, and this is very similar to the acetoacetate synthesis, except we start with diethyl malonate. So if you look now, we're not starting with a beta keto ester, we're starting with a beta diester. So we're one oxidation state higher on this side, and overall we're going to form a mono or disubstituted carboxylic acid. So instead of having a ketone, a methyl ketone on this side, now we've gone one oxidation state higher and we have a carboxylic acid. The individual steps are very similar to the acetoacetate synthesis. So we start with diethyl malonate. We can do deprotonation to form the enolate, and then we can do an alkylation using an SN2 reaction, and so we can incorporate a new R group here. If we want, we can do a second enolate alkylation. So we're going to treat it with base again, and we're going to put another R group. And then we can treat it with acid, water, and heat, or do a two-step saponification of both sides of the ester into the carboxylic acid, followed by decarboxylation to form this mono or disubstituted carboxylic acid. Now just remember that when we do the decarboxylation, we can remove the first carboxylic acid because we have a stabilizing group here. However, even if we heat this with acid further, we're not going to be able to remove this carboxylic acid because there's no way to stabilize the negative charge that results. Now pause the video and predict the major products formed in each reaction. The first reaction is an example of the acetoacetate synthesis, and so we're using sodium methoxide to deprotonate at that carbon. We're then going to alkylate the enolate with allyl bromide, and then we're going to saponify and decarboxylate the ester. So we are going to end up with this product with an allyl group incorporated here, and we're going to then saponify the ester to make the carboxylic acid, and then we are going to decarboxylate. So overall we will remove that entire unit, and we've got this compound here. So if we number the carbons, we've got a 6-carbon chain and a double bond between carbons 5 and 6. In the second set of reactions, we are doing the malonic ester synthesis. We're starting with diethyl malonate. We're doing 2 deprotonations and alkylations. So the first one is incorporating a benzyl group. And then we deprotonate again and incorporate a methyl group. So now we have a methyl group and a benzyl group. And then we're going to do base saponification, so we're going to end up with this intermediate, so this dicarboxylic acid with a methyl group and a benzyl group here. And then in the next step we're going to decarboxylate, so we're removing one entire carboxylic acid, and our final product is going to be this disubstituted carboxylic acid.